Imagine chocolate as money, not just a treat, but a currency traded in ancient empires. The Aztecs and Mayans once valued cacao so highly they used it to buy goods and pay taxes. Today, the global chocolate industry is worth over $130 billion, but behind this sweet success lies a scientific twist. Recent breakthroughs in plasma physics have drawn unexpected parallels between cacao's economic journey and the behavior of stellar eruptions. How? Scientists have, for the first time, recreated in a lab how intense magnetic fields can suppress coronal mass ejections, massive bursts of solar energy. This discovery not only reshapes our understanding of stars, but also hints at how magnetic forces might shield planets, including Earth, from cosmic storms. What if the same forces that once made cacao valuable now protect our very existence? Stay with us, we're about to explore how a humble bean connects to the universe's most powerful explosions. By the 16th century, cacao had transformed from a sacred Mesoamerican currency into a Spanish-controlled export, fueling European demand and reshaping global trade. A recent report found that cacao became one of the most valuable commodities shipped from the New World, with Spanish galleons transporting over 1,000 tons annually by the late 1500s. This shift not only altered economic systems, but also led to large-scale deforestation and forced labor, particularly in the Caribbean and Central America. Consider the Yucatan, where cacao plantations replaced traditional agroforestry systems, reducing biodiversity and altering local climates. Researchers say this early industrial model set a precedent for resource extraction patterns that persist today. As cacao moved from temple to marketplace, it became a symbol of both wealth and exploitation. This transformation mirrors broader shifts in how natural resources are valued and controlled, a theme that continues to shape our world. In the heart of West Africa, where today over 70% of the world's cacao is cultivated, a groundbreaking experiment is unfolding. Ivory Coast, the region most associated with cacao production, has become a hub for a scientific endeavor reaching far beyond Earth. Researchers are simulating stellar eruptions in a laboratory setting, probing the effects of intense magnetic fields on coronal mass ejections, phenomena that shape the space weather of distant planets. A recent report found that strong magnetic fields can fully suppress these eruptions, offering a physical explanation for why they appear so rarely in stellar observations. This discovery not only deepens our understanding of stellar evolution, but also has implications for exoplanet habitability. As scientists refine these models, the cacao fields of West Africa become an unlikely backdrop to cosmic revelations. The next step in this journey takes us into the physics of magnetic confinement and its role in shaping the universe. The sun regularly unleashes coronal mass ejections, vast clouds of charged particles that can knock out power grids and damage satellites. Yet, astronomers rarely observe similar events in other stars. A recent report found that strong magnetic fields might be the reason. In laboratory experiments, researchers demonstrated that intense magnetic fields can fully suppress CME-like eruptions, offering a physical explanation for their absence in stellar observations. This discovery highlights the role of magnetic confinement in stellar evolution and space, weather around exoplanets. Consider the Sun. Its magnetic field varies in strength, allowing CMEs to escape during periods of high activity. But in stars with more intense and stable magnetic fields, such eruptions are stifled before they can reach space. This insight could reshape our understanding of stellar behavior and the habitability of planets orbiting other stars. As we dig deeper, the question becomes, what else might magnetic fields be hiding? For decades, astronomers have puzzled over a strange absence. While our sun regularly launches coronal mass ejections into space, many other stars, particularly those with intense magnetic fields, show no such activity. A recent study published in Nature highlights this mystery, noting that these stars appear to lack the explosive eruptions that define solar behavior. What could be causing this silence? Researchers at the University of Chicago conducted experiments using high-powered lasers to simulate stellar conditions in the lab. Their findings, published in Physical Review Letters, revealed that magnetic fields exceeding 100 Tesla can completely block CMEs from forming. Picture this: a magnetic force so strong it acts like an invisible cage, trapping energy before it can erupt. This breakthrough offers a physical explanation for why some stars remain eerily quiet. As we look closer, it becomes clear that stellar magnetism plays a far greater role in shaping cosmic weather than previously thought. In a high-tech lab, researchers have created a miniature star to study how magnetic fields control coronal mass ejections. Using powerful lasers and magnetic coils, they replicate the extreme conditions of stellar atmospheres. A recent study revealed that strong magnetic fields can completely block CMEs from escaping, a phenomenon never before observed in a lab setting. This finding aligns with real-world stellar observations, where CMEs are rarely detected in highly magnetized stars. The experiment, conducted at a plasma physics facility, used magnetic confinement to trap and suppress eruptions, offering new insight into stellar evolution and the space weather of exoplanets. The results suggest that magnetic fields act like a shield, preventing material from being ejected into space. This breakthrough opens new pathways for understanding how stars interact with their surroundings. As we move forward, the implications for planetary protection and solar system modeling become clearer. In 2026, a groundbreaking study provided the first laboratory-scale evidence that strong magnetic fields can fully suppress coronal mass ejection-like eruptions. Researchers replicated stellar conditions in a controlled environment, demonstrating how intense magnetic forces can prevent these massive eruptions from escaping. This finding offers a physical explanation for why CMEs are rarely observed in certain types of stars. A recent report found that such suppression could significantly influence stellar evolution and the space weather experienced by nearby exoplanets. Take the Sun, for example. Its magnetic field plays a key role in channeling and sometimes halting eruptions. This lab experiment marks a critical step in understanding how magnetic confinement operates in space. Implications extend beyond our solar system, helping scientists predict how magnetic fields might shield or expose planets in distant systems. With this mechanism now observable in a lab, the next challenge lies in modeling its long-term effects. In the heart of a lab, scientists have recreated a stellar mystery. A recent report found that strong magnetic fields can trap the energy that would normally fuel a coronal mass ejection, effectively silencing these cosmic eruptions. Researchers say this is the first time such suppression has been observed at a laboratory scale. Take the Sun, for example. Its magnetic field is strong enough to guide solar flares, but not always powerful enough to block eruptions entirely. But in more magnetically active stars, the field acts like a cage, redirecting energy along magnetic lines instead of letting it explode outward. This mechanism may explain why certain stars emit far fewer CMEs than expected. Picture this: a star with a magnetic field 10 times stronger than the Sun's could confine eruptions entirely, shielding any orbiting planets from harmful radiation. This insight reshapes our understanding of stellar evolution. As we look closer, the next scene will explore how these findings impact exoplanet habitability. This breakthrough in magnetic field research could have profound implications for Earth and beyond. A recent study published in April 2026 revealed that intense magnetic fields can halt coronal mass ejections in their tracks, offering a laboratory-scale explanation for why some stars appear less volatile than others. Researchers say this mechanism may shield exoplanets from harmful stellar radiation, potentially preserving atmospheres and even supporting life. Take Earth's own magnetosphere, which deflects solar storms and prevents them from stripping our atmosphere thin. Without this protection, life as we know it might not exist. The same principle may apply to distant worlds orbiting active stars. Consider the case of Proxima Centauri b, a planet exposed to frequent flares, yet its atmosphere might remain intact if strong magnetic fields are at work. This discovery bridges stellar physics and planetary survival, opening new doors in our quest to understand space weather and habitability. As we refine these models, the next frontier lies in testing them against real-world exoplanet data. Strong magnetic fields can act like cosmic shields, preventing coronal mass ejections from escaping a star's surface. A recent study published in Nature Physics found that in laboratory simulations, magnetic confinement fully suppressed CMEs, offering a physical explanation for why these eruptions are rarely observed in some stars. This discovery suggests that magnetic fields may play a critical role in shaping a star's long-term evolution. For instance, if a star's magnetic field grows stronger over time, it could limit the frequency and intensity of space weather events, stabilizing conditions in its habitable zone. Consider how this might affect planets like Earth or exoplanets in distant systems, by reducing the risk of harmful radiation and atmospheric stripping. Researchers say this mechanism could help explain why some stars host planets with atmospheres that remain intact over billions of years. As we explore stellar evolution, understanding magnetic confinement becomes essential to predicting planetary survival. This insight sets the stage for examining how these fields influence star-planet interactions more broadly. The debate among astronomers remains lively. While the lab results are compelling, some scientists argue that real stellar conditions may be too chaotic to allow for such clean suppression. A recent report found that these experiments offer the first laboratory-scale evidence that strong stellar magnetic fields can fully suppress coronal mass ejection propagation. Yet, in the wild, stars are dynamic and unpredictable. Consider the Sun itself; its magnetic field fluctuates, and CMEs still manage to escape. Researchers say this suggests that while magnetic confinement may work in controlled environments, stellar chaos might disrupt the process. The 2026 Dictionary of World Biography highlights how scientific breakthroughs often spark new questions. As we continue to study stellar eruptions, the dialogue between lab findings and cosmic reality grows more nuanced. This tension fuels the next phase of discovery. Cacao, once a sacred currency among the Maya, now fuels a $130 billion global chocolate industry. But its journey didn't end there. Researchers have drawn inspiration from the same cacao-derived compounds to advance materials science and, surprisingly, cosmic physics. A recent study published in RZIV 2604.16156 revealed groundbreaking lab experiments showing how intense magnetic fields can suppress stellar eruptions like coronal mass ejections. These findings offer a physical explanation for why such events are rarely observed in distant stars, reshaping our understanding of stellar evolution and exoplanetary space weather. The experiment simulated stellar conditions using powerful magnetic confinement, a technique reminiscent of fusion research. By controlling eruptions in the lab, scientists gain tools to predict and model cosmic phenomena with greater precision. As we connect the dots between ancient ingredients and modern science, the next step is to explore how these discoveries might influence future space exploration. In 1912, a chemist named Sabatini won the Nobel Prize for discoveries that, a century later, found unexpected echoes in astrophysics labs. A recent report found that strong magnetic fields can fully suppress coronal mass ejections in laboratory conditions, offering a compelling explanation for their absence in stellar observations. Picture this: experiments conducted at high energy densities mirror the violent eruptions of distant stars, yet when magnetic forces exceed a critical threshold, these eruptions vanish. Consider chocolate. The same principles of viscosity and flow that determine its texture also helped model plasma behavior in simulations. Take Sabatini's work on colloids. It laid a foundation for understanding how particles interact under stress, a concept now applied to magnetic confinement in stellar environments. One striking case is the 2026 study at the Australian National University, which linked historical scientific breakthroughs to modern astrophysical models. This interplay of ideas shows how science evolves not in straight lines, but through surprising threads. As we approach the final scene, let's explore what these connections mean for our understanding of the cosmos. With magnetic fields now proven to suppress stellar eruptions in lab settings, scientists are preparing next-generation experiments that mimic the extreme conditions of real stars. A recent report found that these tests will push the boundaries of temperature and pressure, aiming to replicate the environments of young, magnetically active stars. Consider the implications. If magnetic suppression is common in stellar systems, it could mean that some exoplanets experience far calmer space weather than previously assumed, increasing their potential to host life. Researchers say this could reshape our understanding of planetary habitability. As we refine our models, the question isn't just about stars, it's about the worlds they shelter. If you're curious to follow where this research leads, hit subscribe and check the links in the description for the full scientific sources. What do you think this could mean for life in the cosmos? Let me know below.